Namaskar my dear friends. So let's see a voltage reference IC, all about what is voltage IC, its design and developments. We have already seen voltage reference ICs of shunt type. Now we will see series type. Okay. So in high precision voltage series references ICs, what happens is basically you don't need a series resistance to limit the current into the IC. Okay. This will be without this series resistance. The advantage of this particular voltage reference ICs are this can be used in various applications, like you have to give a reference voltage to the ADC. Even microcontroller ADC requires like external voltage references, so that also you can generate with these voltage reference ICs. Even very high precision DACs are there in many systems. You have some comparators or automotive applications are there where you need to have a very accurate voltage references. Okay. So in that you will be able to utilize this particular voltage reference IC, which is of series type. So there are two types that we have already studied. One is shunt type, one is series type. So shunt type we have seen in our previous sessions, previous workshops. Now we'll see the series type. So what we will do is we'll try to take one of the example. Let's say like REF35-Q1. I am going to take this particular IC which is automotive qualified, and with this with the help of this particular IC we will try to understand how we can design a particular schematic, or what is the requirements for the application circuits, and we can fulfill those applications. Okay. This particular IC can also be utilized in your precision data acquisition systems, industrial instrumentations, medical devices, and there are various manufacturers for this particular ICs. You can take up, let's say, Texas Instruments. I have taken some of the pictures here. You have Analog Devices, you have Renesas, so many manufacturers are there which are giving you very high precision voltage references. So let us quickly see what are the different parameters you need to look into before getting into the selection of the voltage reference IC, and then we will see the design and details of this particular IC. Okay. So this will give you a complete understanding of what are the different things, the different parameters that you need to take care of before selecting a voltage reference IC, as well as how many application circuits I will be giving you here, so that you can utilize them directly to design your voltage reference ICs for your particular application. Okay. So let us see quickly different parameters that we need to look into before selecting the voltage reference ICs are, first of all, you have to have a product status, like whether it is active or not. So you need to select a component which is active for, let's say, around 5 years, 10 years from today onwards. Okay. It is good. What is the input voltage range capabilities? Let us say you have to have a reference requirement of 5 volt, then the input range may be, like you will be needing a 10 volt or 12 volt, something like that, or even 6 volt will do. So basically the input supply of this particular IC must be more than the reference that you need, right? Otherwise it will be not giving you the output of 5 volt. Okay. There are various other references are used. Basically, let's say 1.2 volt is used, or like 2 volt is used, or 2.5, 3.3 volt, 3.3 volt, 4 volt, or 4.096 volt is there actually, 5 volt and 10 volt. Basically these are the variations that are generally used in references. Now coming back to the voltage reference output. So voltage reference outputs, these are the outputs that you can take up. Okay, any of them can be one of the output. Okay, what is the supply current that it will be taking, like how much current it can take up at the input side, and what will be the output current that it will give you. Generally all these ICs are giving 5 milliampere or 10 milliamperes, even they are going to give you 15 milliamperes or 20 milliamperes maximum. I have not seen some ICs which are giving more than 20 milliamperes, but still based on our requirement we don't need more than 10 milliamperes of rating. That is more than enough for any applications in ADCs or DACs. Okay. Coming back to other parameter, what you need to take is reference type. So as I am going to explain you in this, we are going to take up series type. Okay. So voltage shunt reference type we have already seen. Shunt reference type we have already seen it, right? Now we are going to see it series type. Now what is the tolerance? So tolerance is basically whether it can be as good as 0.01% or 0.02% or 0.1% or 0.2% or 0.5% or 1% or 2%, something like that. But these are very high in which are 0.01% or something like that. Okay. What is the temperature coefficient? So basically it is in ppms. So let's say it is 10 ppm per degree centigrade or 100 ppm per degree centigrade. So if it is lower, then it is better. Okay, so generally you will be having 4 ppm per degree centigrade, which are very high end ICs, or 2 ppm per degree centigrade, and lower end ICs, they will be going up to around 50 ppm or even 100 ppms. Okay, what is the noise between 0.1 hertz to 10 hertz? So it can be in vrms. Okay, so let us say 4 microvolt RMS per square root of hertz. Like that, it will be giving you the noise. So if it is lesser, it is better. Okay, so temperature coefficient also should be less, noise should also be less. The other thing is operating temperature range, whether it is going to work from which temperature to which temperature. Let's say 0 degree centigrade to 85 degree centigrade, or minus 40 degree centigrade to, let's say, 155 degree centigrade. So it's up to you. Based on your application, you will be selecting your particular IC. What is the mounting type, whether it is a surface mount type or through hole type, and it must be RoHS compliant. Okay, some of the IC series or something like that, if I give you, then you can take up. These are the, like, numbers that you can take up. Let's say LT1236 or LT1027, REF35-Q1 or REF4132-Q1. These are not the complete part number, these are the first initial part numbers. Based on the voltage rating, the extension will be coming. Okay, so voltage ratings, as I told you, these were the voltage references. So based on these voltages, there will be different ratings. Okay, extensions. So as you can see, we have REF4132-Q1, then REF5050A-Q1, we have ADR586, we have ADR3430. So as you can see very clearly, if it is, let's say, 30, then it is going to give you 3 volt. If it is 20, then it will give you 2 volt. If it is 40, then it will give you 4 volt. Like that it is going to come, right? ADR353630 is there, then ADR3630 is there. One of the best IC that I prefer, this one is. I will be explaining you some 3 or 4 of them as well after this session. Okay. We have LM4128-Q1. So these are some of the ICs that I had given you as a part numbers. You can have a look in their data sheet and try to understand after comparing this particular session. Okay, so that you have a better understanding to become a very good hardware engineers, or like whatever the applications that is there in your mind or in your industries projects that you can take up. Okay. Now let us get into the understanding of this particular IC that we have taken up, which is going to be REF35-Q1. So this is from Texas Instruments. Texas Instrument. So I have given the link for like product page and the data sheet, so that I will be giving you in the like comment box as well in the description. Now going back to the features of this particular IC, it is very easy to understand by like data sheet. So this is very like ultra low power high precision voltage reference. This is AEC Q100 qualified, means it is automotive applied. Okay, automotive qualified it is. It has a temperature range of working from minus 40 degree centigrade to 125 degree centigrade. It can take up a very low ultra like low quiescent current, which is going to be just 650 nanoamperes, less than a microampere even. Then it has initial accuracy of plus minus 0.05%. The temperature coefficient is plus minus 15 ppm per degree centigrade. Not that great, but it is okay. It has output noise, which I told you 0.1 hertz to 10 hertz is just 3.3 ppm. Okay, and it has NR pin to reduce noise. So there is some NR pin which is going to have one capacitor which will make sure the like it has reduced noise. So if you want to reduce the noise, you can put one capacitor at the NR pin, which will help you to suppress the noise. It has enable pin to reduce shutdown current consumption. So it has some enable pin which can make sure that the IC is shut down. Otherwise you can leave that open also, no problem. We have 1000 hours at 30 ppm. Okay, so very long term stability is there. It has a storage temperature and operating temperature is 125 degree centigrade, that we already told you, right? It has output current capability of plus 10 milliampere is sourcing of capabilities, and minus 5 milliamperes is sinking capability. So it can sink current also with 5 milliamperes. And voltage input it can take up V reference plus VDO to 6 volt. So 6 volt is the maximum input that it can take up. Otherwise the dropout voltage is there, which is around 300 millivolts. So that much plus V reference that you want, that will be needed. Let us say you want 2 volt reference output, then you need to give 2 volt plus V drop. So let's say 200 millivolt. So just 2.2 volt will be the input, and you will be getting your output to 2 volt. Understood? So just 200 millivolt drop will be there. That I will tell you exactly in the data set it is given. There are various output voltage options for this particular IC, series, which is REF35, which you can take up 1.2 volt, 1.25 volt, 1.8 volt, 2.048 volt, which is close to 2.1 volt, and 2.5 volt, 3 volt, 3.3 volt, 4.096 volt, and 5 volt. And it is very small package, which is SOT23 package. As I already mentioned you, these are the ICs which are used in basically ADCs or DACs as a voltage reference requirement, right? So it can be utilized in your automotive front cameras. It can be utilized in driver monitoring systems. It has application in battery control units as well as electric power steering or something like that. So basically all the automotive applications you can utilize this particular IC as a reference voltage. Okay, so coming back to the device information. So device information is basically going to be like this: REF35 XXX is basically going to give you the voltage rating, that is you have to select, right? And this is SOT23-6 type. So basically it is having 6 pin with SOT package. This is the IC that it looks like. It is very small package, which is just 2.9 mm to 1.6 mm. Coming back to the application circuit, how we are going to design our application circuit is nothing but, if you want, you can put your enable pin to connected to input so that it is always enabled. Otherwise you can leave it open also, then also it will be enabled. If you pull it down, then only it will get disabled. Okay, so you have to make sure that if you want to shut down this particular IC, then you have to put a microcontroller IO or something which will pull it down to shut it down and pull it up to you give it output, right? You just need one input capacitor. You can have one more additional 10 microfarad capacitor for better transient responses. And at output you can have 1 microfarad, or even little bit higher you can keep, let's say 10 microfarad plus one additional 0.1 microfarad you should give, so that it can give you a filtered output. So this is your V reference that you will be getting. So this is the exact design that you can put additional 10 microfarad this side and additional 10 microfarad plus 0.1 microfarad at the output side. You have NR, which is going to be, let's say if you generally by default you put it 0.1 microfarad, that is more than enough for a very good smooth output. Now let us try to understand what are the use cases of this particular IC and how you can make yourself understandable to understand how it can be utilized in your different uses, right? So let us say we have a current sense amplifier, which is let's say INA 181 or something like that, okay, or some other are there. So suppose they need some reference input. In that case you can utilize this REF35-Q1 IC to give reference voltage, okay, and this is how it is going to generate your reference voltage, and it will give you a current sense output amplification, correct? Some other ICs you can take up. I don't remember exactly the numbers of current amplifier. However, this is used in this particular segment. So you can see amplifier biasing for CSA, INA, DFA, ETCs. Coming back to the other application, which is going to be sensor power supply, bridge or thermocouples. Okay, so sensor powers you need, there also you need to have some reference voltage. In that case you can utilize this particular IC, as well as I already mentioned you ADCs and DAC references. This is one of the best IC, or generally voltage reference ICs are used as a reference voltage generator for the ADCs and DACs. Okay. Coming back to the part number of this particular IC, so as I told you, last 3 digits is going to give you the voltage reference value. So this is 1.2 volt, it means 120. 1.25 volt, this means 125. Got it? Similar to that, if it is 4.096, then it is 409. Okay, so this is how you are going to have the part number of this particular ICs for your respective voltage reference. So if you need any part number, you can take a screenshot of this, or you can go to the data sheet and find out device comparison, and where you will be having all these part numbers for different voltage references. Okay, so this IC can give you a 1.2 volt to 5 volt variations. Okay, so these are the different part numbers for different voltage references. Okay, now let us get into the design mode, like how we can design circuits using this particular IC. So for that we have to understand the pin configurations and pin functionalities. Okay, so if you talk about your pin configuration, you have 6 pins which are like ground pin, and we have enable pin. So we are having 2 ground pins, 1 enable pin, and we have voltage reference output. This is your NR pin. NR pin, you can see this is my NR pin, which is pin number 5, which is going to be noise reduction pin. So you can connect one capacitor to reduce the noise. Okay, and this is your input supply. So this is your input supply, V input, and this is your reference, which is going to be V output. Okay, that's all. Two things are there, which is more than enough. You don't have, you just put grounding over, and you have to, if you want, you can put one NR capacitor to reduce the noise. Okay, you can leave this enable pin open, there is no problem at all. Otherwise, you want, you can connect it to the input voltage. Okay. Coming back to some of the like electrical parameters, so let us talk about absolute maximum rating. So absolute maximum rating, input voltage is very important, so it can take maximum 6.5 volts. So your aim must be, as a designer, as a good designer, what you need to understand is any ICs are having their limiting values or the absolute maximum ratings. So there you need to make sure the input voltage must not exceed this voltage, otherwise the IC will get damaged. Okay, so that's the reason absolute maximum ratings are very, very important. Same way, enable pin also can take up to your input voltage plus 0.3. It should not exceed more than input plus 0.3 volt. Okay, similar to that, output voltage, it can give you output voltage which will be not more than V in plus 0.3, otherwise it will again get damaged. We have output short circuit current, which is maximum 20 milliamperes, otherwise it will get damaged, right? And you have the operating temperature range, which is up to 125 degrees centigrade and minus 55 degrees centigrade on lower side. Okay, but these are the absolute maximum ratings. Now we have to understand about recommended operating conditions. So in this case only we have to understand this. Generally we should like take this into account, not that one. Okay, so input voltage is up to 6 volt, and minimum voltage will be required whatever reference output that you want plus voltage dropout. Got it? And we have enable voltage, which is going to be just up to V input, and we have output current, which is going to give you minus 5 milliamperes to 10 milliamperes. Okay, and we have operating conditions, which is up to 125 degrees centigrade, and lower side it is minus 40 degrees centigrade. Okay, so you can see for 1.2 volt and 1.25 volt we have requirement of input of 1.7 volt. Okay, and VDO is your dropout voltage, which I told you. So as you can see, you can calculate that 1.7 minus 1.25, so that much voltage is your V dropout between the IC. For higher voltage the dropout can be reduced, but for lower voltage you need to give minimum 1.7 volt. Okay, coming back to the thermal information. So thermal information, as you know, the voltage drop across the IC, let's say this is my V input, this is my V output, which is your V reference. Okay, so whatever the voltage difference between these two is there, plus the current output that you are going to take, so let us say delta V multiplied by the I out is going to be your PD. Okay, that is your power dissipation across the IC. So what will happen is, this power dissipation is going to heat up the IC, and this is how the temperature will be increased. So for 1 watt of power, you are going to increase 164 degrees centigrade temperature. Okay, so basically let us say you need 5 volt output multiplied by 1 milliampere, so this is going to be 5 milliwatt. That's all. So 5 milliwatt is very, very less. So if you have, what is the temperature range that will increase? So let us say delta T we want to calculate, like what is the temperature increment that will happen with this much power dissipation. So we have the value of thermal resistance, which is going to be 164 multiplied by we have this much power dissipation, right? So that is 5 milliwatts. So 5 into 10 to the power minus 3. Okay, so it is going to be, let us say, 160. So 160 into 5 is 800. So 0.8 degrees centigrade, that's all. There is no increase at all. Okay, not even 1 degree centigrade. So this is how you are going to have a good understanding about thermal information for any ICs. Okay. If you didn't understand this, then also no problem. You can just calculate your power dissipation across the IC and multiply that power dissipation into the thermal resistance. So you can see this is degree centigrade per watt and this is milliwatt. So watt got cancelled. So that's the reason it is degree centigrade remaining. So that much temperature will be increased based on the voltage drop across the IC. Okay. Coming back to the electrical parameter for other parts, let us say we have output accuracy. So output accuracy, you already know that it is plus minus 0.05 degree centigrade. Before studying this electrical characteristics, you have to understand your input voltage must be V reference plus 0.5 volt. Okay. So let us say you want to have a 5 volt output, then you need to give input minimum 5.5 or otherwise up to 6 you can give. Your enable pin is V input, your load capacitance is 10 microfarad, your input capacitance is minimum 0.1 microfarad, and you have load current minimum 0 milliamperes. Okay, this is how, these are the conditions that is there. Okay, you can see we have line regulation, load regulation. If you want, you can have look into these parameters as well. Some other parameters are input voltage, which will be minimum V reference plus V dropout, that we have already talked about many times. We have quiescent currents, which is very less. You can see based on the temperatures that they give, like at 25 degrees centigrade it is just 0.65 microamperes, but if you go for little higher range it will be little higher, which is 2.6 microamperes. Okay, we have enable pin which will be required minimum 0.7 times V in, otherwise it will be problem. Otherwise you can leave it open. Either you give minimum 0.7 times V in, otherwise directly you can connect it to V in. Let us say you have to have a voltage input of 5 volt, then minimum input must be how much? 5 7 5 is 3.5 volt, otherwise it will not switch on. Okay, or else what you can do is you can keep it floating, like you don't need to connect to any voltage to the input to the enable pin, so that it can be fine. If you want to put it in shutdown, then you have to ground it. Okay, similar to that other parameters are there, that is nothing to worry about. We have like short circuit current and short circuit sinking. So this will be maximum 33 milliampere and this is 21 milliamperes. Okay, coming back to some other parameters, last one which we have like noise. So output voltage noise is just 0.7 ppm RMS, and 1 hertz to 0.1 hertz to 10 hertz I already told you, which is 3.3 ppm peak to peak. Okay, good. Coming back to the some of the characteristics. So characteristics, if you see, this is the temperature drift that will be there based on the temperature. Okay, so as you can see we have output voltage drift versus free air temperature. So as my temperature increases, the drift is actually increasing. Okay, so drift is in ppms. You can see at let's say around 25 degrees centigrade it is almost zero drift, but as my temperature increases my drift is increasing, which is going to be almost minus 1000 ppms. Okay, coming back to the load regulation. So load regulation is almost plus how much it is, minus 7%. Okay, so minus 7, not it is not 7%, it is ppm per milliampere. So minus 7 ppms per milliamperes. Okay, which is very less. It's not a problem at all. Up to 125 degrees centigrade it has less than plus minus 4 ppm or something like that. Okay, coming back to the load transient response. So what happens in load transient response is basically, let's say you have a load of 1 milliamperes and we have reference of like this much voltage. As my load directly suddenly increases or decreases, what happens is there is a glitch, or there is a like sharp transient that will be there in your reference voltage, which is less than how much it is. Since it is 50 millivolt per division, it means it is just around 50 millivolt plus minus. So 50 millivolt there will be a difference at the a response time. If it is 10 milliampere load, then it will be close to like a 200 milliampere or 200 millivolt difference. Okay, so you have one of the characteristics that is shown for 2.5 volt reference, that the difference will be almost like 2 to 300 millivolt. Okay, just at this particular start point, otherwise it will be again stabilized after some time. Got it? So after less than a millisecond, 1 millisecond is the division, so less than a millisecond it gets stabilized. So you have to give a time of less than a millisecond if there is a sudden change in the load. Coming back to the power supply rejection ratio. So power supply rejection ratio, you can see up to around uh, how much it is, 100 kilohertz, you have around 60 dB, more than 60 dB. Okay, so up to 10 kilohertz and all, you have very good understanding, like very good PSRR, which is more than 80 dB. But as you go on little bit higher frequencies, let's say 100 kilohertz, then it goes to 60 dBs. So this is also very good response, not a problem. As I was telling you about the dropout voltage, so my V input must be greater than V output by a amount of voltage which is called V dropout. Okay, so this dropout voltage will be varying based on the temperature. So as my temperature increases, my dropout also increases. So as you can see, for 125 degree centigrade and 10 milliamperes of current, or 10 milliamperes of current, it is going to be just above how much it is, 150 millivolt or something like that. Okay, so 150 millivolt is maximum voltage dropout that you are going to see. Good. Now let us get into the design and power dissipation. So power dissipation, as I told you, the theta RJA was there, like R theta was there, multiplied by power dissipation, and total temperature of the IC at junction will be how much? Like temperature at junction will be this much, plus this is your delta T, right, plus the temperature of ambience, which is maybe, let's say, 25 degree centigrade of your environment temperature, or maybe 30 degree centigrade, that much you can add. So that will be total temperature at the junction of the IC. Okay, so this is very simple, as I already have I have given you the example. Let's get into the block diagram of this particular IC. So block diagram, if you see, let me make it little bigger. Good. So we have input voltage, we have enable pin, which we can write it, I mean put it directly to the input voltage with one of the resistance. That's not a problem, because since this is like open drain control, so if you want to control through one IO pin or something like that, like GPIOs of microcontroller or something, let's say you want to shut it down or something like that, then you have to have a pull up resistor here. Okay, so RP is a pull up resistor, you can put it, let's say, 10 kilo ohm or something like that. And this is your input voltage. We have ground pin, we have NR pin, which is noise reduction pin, and we have your voltage reference, which is going to be your V output. Okay, so what is the thing? Simple. We have input voltage, we have enable pin, which is going to give you a digital core, and which we have band gap core, and these are the two things which are going to get enabled and going to give you the output with buffered. Okay, so there is no need of your external buffers. Okay, coming back to the next parameter, which is going to be enable pin. So as I already mentioned, it can be connected to the V input pin or left floating. It can be used as a shutdown pin also. To pull it down, you have to pull down the enable pin, and to use it as output pin, you have to have a open drain condition. So in that case, you have to pull up with the V in. Okay, coming back to NR pin. So NR pin, as I already mentioned you have to put a capacitor from NR pin to the ground so that the overall noise can be reduced. But the problem with this capacitor addition is, as you add a capacitor to the NR pin, the start time will increase. Okay, so startup time, let's say it has taken earlier 1 millisecond, now it may take around 3 millisecond or something like that. Okay, so because the capacitor will take little bit time to charge, that's the reason the adding a capacitor will also increase the startup time of the IC. Okay, coming back to basic connections. So as I already mentioned you have to have an input capacitor, we have to have an output capacitor, and we have to have an optional noise reduction capacitor. That's all, nothing more than that is needed. And as you can see, we have input voltage here, we have voltage reference output, so that is going to take just less, like this is complete is 5 millisecond, which is 5 millisecond per division. So it takes less than like a 2.5 millisecond. So close to 2 millisecond will be the difference from input to output. So just after 2 millisecond you will be able to get your output voltage. Now let me give you the basic connection of a particular application. So particular application, if I tell you, you have to have a basic connection like this. Exactly you implement this particular circuit, this will definitely work. Okay, let us say you have a output voltage of requirement of 2.5 volt, then you must give a, like input voltage, let's say 3.3 volt or 5 volt. Okay, and 10 microfarad of 16 volt will do, even 25 volt will do. 0.1 microfarad, always try to use 50 volt rating because it is very abundantly available, very abundantly available, like it is very common. But 10 microfarad you can utilize up to like 10 volt or 16 volt ratings. Got it? Noise reduction pin also you can put 1.1 microfarad capacitor, or otherwise leave floating, so that it will be the output. So this is the complete design of any circuits that you are looking for your application circuit. Coming back to the application of negative reference voltage. So let us say you want to generate one like plus minus 2.5 volt negative reference voltage. So for that, what will you do? You will utilize the IC REF 250, sorry, REF 35250. So 250 is going to give you 2.5 volt output, right? Now what will you do? Suppose you want to generate a negative voltage reference also, then you will take with a inverting amplifier. So in that case, what will happen? This 10k and 10k is going to take this voltage as input voltage, which is going to be 2.5 volt, and this with a unity gain like 10k 10k, it is going to give you minus 2.5 volt. So if you want, you can utilize OPA series of like op amps for this particular purpose. And this OPA ICs can be used as like OPA 2180 or 2277, little bit higher cost are there. 2205, 2206, these are very good ICs but bit higher cost. Lower cost you can utilize OPA 181 or 188 or 189, OPA 181 or OPA 182, 187, something like that are good ICs. Okay. Now let me tell you a precision application or precision power supply application for your ADCs. So what happens is ADCs or DACs, basically we need to have one input. Let's say we have a measurement input which is going to be like measured at ADC. Okay, so these are the voltage that is going to go into, and this is my buffer that is basically used, and this is going to get into the ADC IC. So this is my ADC IC. Any IC that can be used, but the thing is it needs a reference voltage which we will be generating from the voltage reference IC. So this is my voltage reference IC which is generating the voltage. So this is my input voltage to the voltage reference IC. These are the two capacitors that I am using. So capacitor, always try to use 0.1 microfarad and 10 microfarad. This is always like a normal values. Okay, and output you are going to get at this particular pin, which is going to be pin number 6. Okay, so this is my output voltage. So this V reference is going to be a reference input for this ADC, and this is how you are going to get your ADC output for this particular inputs. Okay, so these are the voltage to be measured. So this is measured voltage that has to be measured at the ADC, and this is how the connection will be there. So you have a requirement of voltage reference to the ADC. For that you are going to use a voltage reference IC to generate the voltage reference. Okay. So let me give you a design process of any circuits like this. What happens basically is we have a design requirement of what is the like input voltage that we need. So let us say we have to measure a voltage from 0 volt to 3.3 volt. So definitely you need an voltage reference IC which can measure up to 3.3. So you have to have selection of 3.3 volt or 4.096 volt or 5 volt. So these are the two good references that will be there for this particular range, right? Then what is your reference input capacitor, reference output capacitor? If you want, you can have current as well. So anyway, current doesn't matter here, so it is not a problem. If you need current more than 10 milliampere, then you can utilize a different circuit that I'll tell you in the next session. Okay, let's say you need 100 milliamperes of current at the output. So in that case, you can utilize some extra amplification with one MOSFET or something like that, so that it will be giving you 100 milliamperes as well. Okay. Coming back to last, which we need to take care of while designing any circuit in your industries, is layout guidelines. So if you're going to get it designed to the PCB, then what you have to do, this is the particular IC that we are talking about. So we have two ground pins, okay, and we have enable pin. So through enable pin you have to have a like a bias, and by bias you are going to get connected to input voltage. Okay. Similar to that, we have NR pin, which we are going to take up here, and one capacitor you can add to the ground. So this is complete ground. Okay. And you can you don't connect capacitor here, otherwise there will be a problem, very big loop will be there, so this is not recommended. Okay. So connect capacitor like this, and then output capacitor, sorry, this is my input capacitor, so input capacitor will be like this. Coming back to the output capacitor, so this is my V reference. So V reference, here output capacitor will be there as close as possible to the IC. So two capacitors, it can be connected like this, one more capacitor will be there, and similarly to that, one more capacitor will be coming here, which will be, let's say, 10 microfarad and 0.1 microfarad. Similar to that, this will be 10 microfarad and 0.1 microfarad. Okay, and this will be, let's say, my 0.1 microfarad. So this is complete design that you need to have, but you must have a bias or something like that, so that you can take it to the input and make it enabled. Okay. So alright guys, if you have any questions on anything something like that, you can put down your questions in the comment box, and we shall be able to answer you out any queries something like that. Application details we will be discussing in the next session with ADR 34XX or 35XX or 36XX. So I'll try to give you one more data sheet so that you have a complete understanding about how does this particular voltage reference works. Okay. And please try to understand what are the different parameters that we need to look into before selecting a particular IC. Otherwise there will always be a deficiency in your design. So if you want to have a very sturdy, very accurate design, you must know all the parameters that I have explained you in this particular session one by one. You can go through the videos again and again to understand each and every details slowly. Okay. So thank you so much.